strange things that you've not seen before. Okay? Or probably not seen before. But that's fine. That's good news. Try to recall which ones we've done and not done. Did we do one with a box where you cut out tabs? I know the other class did. I'm trying to keep tabs of. Okay. So let's go after that one first. Okay, so example 1. We'll start out with stuff that's a little easier, and then we will work into things like inventory control. We will work into things like controlling your costs while maintaining your inventory. Is that something that a business would be willing to pay you for? Yeah. Those are a little more complicated. We'll work toward it. Okay, let's start out with something fairly straightforward. Let's see. We're in November. So obviously all the candy companies are thinking about what? You're right, Easter. Way to go. Okay. What? Why are the candy companies thinking about Easter? Christmas is way done, dude. That was back in August. They produce the product, move it to their warehouses, ship it out to other warehouses like Walmart and Target and wherever else, Kroger's, and then from those warehouses, that stuff's all in the store now, isn't it? Christmas candy, it's been there for a couple of days or weeks. Right now, they are turning more toward Easter. Christmas is done in their mind. Okay? I don't know if you've ever seen it or not, but one of the types of boxes that they make is where you just take a piece of cardboard and you fold the 4 sides up. It's kind of a lightweight box. They use it for holding a ton of Easter candy, stuff like that. The way those boxes are made, the way the base of that box is made, is you take a rectangular piece of cardboard and you clip a tab, a square tab, off of each corner. Okay, they use dies and you just stamp them, boom, cut them out. You can imagine as being with scissors, cut them out. And then you take the 4 sides. Okay, so here would be one edge, here would be another edge, here would be an edge, here would be an edge, and what will wind up happening is you now have a piece of cardboard. After you remove those 4 corners, you have a piece of cardboard that's cut like this. And when you take those 4 tabs and you fold them up, put a little piece of tape on each corner, and ta-da, you have the base for a box. Does that make sense to everybody? Okay, with this box, you know that the volume needs to be, let's say, 8 cubic inches, and the base needs to be square. Square, oftentimes for marketing reasons. If it's square, the box has a little different look to it, or square because you know how much footprint you're going to be allotted on a shelf in a store. Ooh, is that important to keep in mind? How much shelf space you're actually going to have? Yeah. So the base of the box needs to be square so that your product is looking the way you want it to look. Needs to be able to hold 8 cubic inches. Is that a lot or a smaller box? Is this going to be a big box? It's going to be one where you spread both arms and tie into it? Or is this going to be something you can pick up with one hand? Well, a cubic inch is a little wooden block. So 8 of those is not real big. So this is going to be a smaller box. So it might be something like for the Cadbury eggs or something like that. Okay. The objective here is to minimize the amount of cardboard needed to build this box. Let's say we're going to throw gourmet jelly beans in it. So whatever the dimensions of the box are, you can fill it with the jelly beans. They'll fit nicely. Okay? The objective is to make the box as inexpensively as possible. Now, when the problem is posed to you, it's not going to be, we want to minimize the material. Because that's not the way the average person thinks. They think at this upper level, this more superficial level, trying to save money. How cheaply can we make the box? But what you need to hear that translated through a math filter as, if the box is going to be less expensive, that means we're going to need to use less material. Does that make sense? The less cardboard you use in the box, the less expense there is. So even though what is stated is we want to control cost, or we want to keep costs down, a way to keep costs down is to minimize the material. Okay, so the superficial level, control costs. One level down, minimize the material. How are we going to measure the amount of material used? Well, the material makes up the surface of the box, doesn't it? Aha. So first level, minimize cost. Second level, minimize the material. Where we're really going to be working is down a level lower, which means that we want to minimize the surface area. Does that make sense, how you have to step it through several levels, if you would, to get to where we really need to work? Well, why do we need to go to surface area? Okay, if we were to stay at the level of material, how could you write an equation to describe the material? Well, maybe. But moving down to the surface area, could you write an equation to describe surface area? Yeah, the surface area, you could make a list. It's going to have the base plus it's going to have 4 sides. And computing the area of the base is no big deal for you. How do you compute the area of a rectangle? Length times width, isn't it? The sides, oh, those are rectangles. Length times width. So what we've done is we've taken it from, hey, we want to control cost, to a new situation where you know what the formulas are and it's easy enough to work with. Okay, so we want to minimize the surface area. Now, the 4 sides in this problem are all going to be the same size. Well, Chuck, I don't know if I buy that or not. Okay, we're going to have a length, we're going to have a width, and this piece right here is going to establish what will be the height of the box when you fold it up. When we put in the condition that the base is a square, okay, when we make this statement here, what does that do with our length and our width? Makes them equal, doesn't it? So the fact that the base is a square is going to allow us to say, hey, the length equals the width. That's another one of those little sneaky maneuvers that you're picking up in here. Folks will sometimes say, well, we need a box that's square. The whole thing square or just the bottom? Oh, just the bottom. It'll be whatever height it needs to be. And folks will sometimes overlook that by saying it's got to be square, that tells you right off the length and the width are the same. It's not that folks don't know it, it's just that they've not been trained to think like that. And to realize that, aha, as soon as you say square, boom, I get some stuff for free. Now this is really handy because what we can do then is we can come back to our diagram on the left, and if we call this the length, what was being labeled as the width can now also be called the length, or the width, whichever we want to do. And there's a purpose in relabeling it as a length as well. And that purpose is, originally it would have been the base has an area length times width, plus each of the 4 sides, well, two of the sides are going to be the length times the height, and two of the sides are going to be the width times the height. How many different variables are there? Let's see, we have length, we have width, we have height, three variables. Do you know how to well, wait a minute, when you optimize, how do you optimize? How do you find max mins? You take the derivative, set it equal to 0. Do we know how to do derivatives with three variables yet? No, that's in store for January. Okay. So after Christmas and New Year's, when you come back, that'll be the first thing we go after is, what do you do when you got 3, 4, 5, 50 variables in the equation? But we're not there yet. Okay. We haven't gotten past Thanksgiving, let alone Christmas or New Year's Eve. So we got to get this down to, well, everything we've done just involved one variable. So we need to get this down to one variable, realizing that length and width are the same. This can be rewritten where I'm going to take each width and replace it with L. Gosh, Chuck, how'd you know to replace width with L? I just picked one of them. Could we have replaced length by the variable width? Yeah, that would have worked fine. Okay, so when we do this substitution, it's going to give us L times L plus 2LH plus 2LH. Oh, wait a minute. This cleans up a little bit to be L squared plus, if we have two of these, plus two more of them, it's going to give us 4LH. We're down to two variables. We're getting there. We started with 3, we're down to 2. We need to get down to how many variables, though? I guess 1, since that's what we know how to do derivatives with at this point. Okay, so how are we going to get rid of one of those variables? Well, if you go shopping through the information that we have up here, notice we have that the volume equals 8. Do you know how to figure out the volume of a box? Well, sure you do. Recall that volume is length times width times height. And in this case, that has to equal 8. And you know a little bit more. We know that the width is the same as L, so this gives us L squared H equals 8. And you can solve for H as 8 divided by L squared. Does that make sense? This H, which is 8 divided by L squared, can be substituted in right there, which will allow us to rewrite our surface area as L squared plus 4L times 8 over L squared. This then gives us L squared plus 32 over L. Is everybody okay with how that worked out? The L in the numerator cancels with one of the L's in the L squared, which is in the denominator. Okay, and I'm thinking ahead. If I want to minimize this surface area, I'm going to have to take the derivative. Yeah, if I'm going to do derivatives, I'm going to rewrite that as L to the negative 1. How much calculus have we done so far? We're about 15 minutes into the problem and we've done no calculus. Calculus is one of those things that oftentimes will just come in for one step, saves the day, and then right off into the sunset. Well, algebra is doing all the day-to-day work. want to do is we want to minimize the surface area, which means that we need to compute the derivative. Well, that's going to be 2L minus 32L to the negative 2. Does that look familiar? There was the calculus. That little blurb right there was all the calculus. Then what we're going to do is take the derivative, and let's see, what's always the maneuver for minimizing or maximizing? You take the derivative and set it equal to 0. So what we're going to do next then is we're going to take our 2L minus, and I'm going to rewrite this as 32 over L squared equals 0. We're back to algebra, aren't we? This is then going to give us 2L equals 32 over L squared. How do we solve for L here? What are we going to do? What's our move to solve for L? Well, how about multiplying both sides by that L squared, which will give us 2L cubed equals 32, which will give us L cubed equals 16. Uh-oh. This means L is going to be equal to, the cube root of 16. Should I leave it as a cube root, or should I get a decimal? I would suggest getting a decimal, yeah. Because we got to cut something this length, don't we? Imagine you went to Lowe's and said, I need some chain. Okay, well, we've got a big long coil. How much do you want us to cut off? Oh, I need the cube root of 16 feet. How's that going to work? They're going to kind of look at you and maybe call security. Okay. So let's convert it back to a decimal. 16 cube rooted, which is raised to the 1/3 power, is 2.52. Is this going to be feet, inches, yards, miles, days, hours? What are the units on this? 2.52. Inches. Good. Okay, now at this point it's very tempting to come back up and say, hey, we've got it made. We know that the length in that box is going to be 2.52. The width, that's just the length again, 2.52. And then the height, the height we can solve for by plugging in 2.52. However, before we do any of this, what do we have to make sure of with that 2.52? Maybe make sure it's the minimum and not the maximum? Because if we're maximizing the material, that means you're maximizing the cost, and somebody's going to be back to talk to you about that. Somebody somewhere along the line is going to realize, hey, Chuck's really messing up back there. He's costing us a lot of money. And remember, when you're doing this stuff, you're not just thinking a box. It's like Campbell's soup. How many cans do they make a year? Close to 7 billion. So if you mess up a little bit, times 7 billion, that's a whole lot of mess up. Okay? So there's no tolerance for messing up on this stuff. Okay, so we need to first verify this is a minimum. Okay, verify it's a minimum. You got two ways to do that. One way is to create a number line, put your 2.52 there, and evaluate the derivative on each side of this. Does this look familiar? Okay. derivative, here it is. Well, I really can't use 0 because that'll cause it to be undefined, so I guess I'll have to change that up to 1. So what this is going to give us, f prime at 1 is going to be 2 times 1 minus 32 over 1. I don't care what the number is. Is it positive or negative? 2 minus 32 is definitely negative, isn't it? Aha. So that would give us negative there. F prime at 4 is going to give us 2 times 4 minus, let's see here, this is going to be 32 over 4, and remember that's 4 squared. That's going to be 8 minus, let's see, 32 divided by 16 is less than 8. Oh, that's going to be positive. Okay, so the function is going to go from decreasing to increasing. If you have a scenario where you're going from decreasing to increasing, the function attains a max or a min. See, it's going to be a min there? Because it's going down and then back up. Okay, so this is going to be a minimum. And you're good. Ta-da, you've proved that it really is minimizing. Does that make sense to everybody? What would have been another way to verify that we're minimizing? Second derivative? Okay. To do the second derivative, we would have come back up to here. I'm intentionally doing this both ways just to remind you that you have options. The second derivative is going to be 2 plus 64 L to the negative 3. This is going to be 2 plus 64 over L cubed. Now, I'm not even going to bother plugging numbers into that because we know the length has to be positive, doesn't it? Can you have a negative length on a box? Yeah, not so much. So all we need to know is L is going to be positive. If L is positive, L cubed will be positive. 64 is positive. If you have a positive divided by a positive, that's positive. Plus 2 is positive. This thing has to be greater than 0. Now, if it's greater than 0, positive, that means I'm smiling. Concave up. If it's concave up, what do you have? A minimum. Okay, so either way, we have verified that we have a minimum. Well, gosh, which way do you want me to do this on quizzes, tests, final exam, things of that nature? Whichever way makes sense to you. Yeah. Yeah, if it wasn't a minimum, that would have meant, that's a good question. Yeah, what do we do if, and it happens at times. And if it turns out to be a maximum instead of a minimum, that means something's messed up in your equation or something is messed up in your derivative. So you got to go back and start checking through and making sure that things really are what you were hoping they were. All right. We know that the length is basically 2.5 inches. The width is 2.5 inches. So the box is going to be about that big square. The question now is, how tall do we make it? Well, to get the height, we're going to use this equation, 8 over L squared. Okay. So to compute the height, we're going to have the 8 over 2.52 squared. And if you run that through quick like, 8 divided by 2.52 squared, I got 50. Should have done 8 divided, not 8 11.26. Okay, so what you're going to wind up with here is a little box. It's about 2.5 inches wide, 2.5 inches long, and about 1.25 inches tall. Have you seen the little boxes that have like 4 or 5 pieces of the Brock's chocolate in them or something like that? That's the box. That's the box that we're working on. You mean this really happens? Yep, that's a real box. Does that make sense how to do that one? Let's go after another one. On Friday, I'm going to bring in a paper and it's going to have 8 or 10 different types of problems. Some of them are going to be figuring out how do you price tickets. Things like how much inventory do you order at a time and keep in storage. A variety of problems like that. When they price a ticket, they just pick a price, right? There's been a lot of work go into the price for that ticket, if it's a concert or whatever it is. What they're after is not to bring the most people in. They're after bringing in enough people that will optimize the profit, which is very different from bringing in the most people. If they wanted to bring in the most people, wouldn't they just charge 0 for admission? That would bring in the most. Okay, had mentioned Campbell Soup, 7 billion cans. Let's design a can. First off, why are cans round and not square? Never really thought about it, Chuck. It's cheaper to make for one thing. But if they were square, when you put them in a box, wouldn't it completely fill the box that way? When they're round the way they are, you got all kinds of empty space in there. So space-wise and packing-wise, the shape of the can is not the most efficient shape. And in designing and deciding on that shape, they had to weigh how much space do we want to lose versus how much material do we want to invest in saving that space. Structurally, which is stronger? On the joints and things, the circle is. So there are all kinds of considerations that went into even deciding, you know what, cans are going to be this shape. Cheaper to make them circular. So all kinds of things went into it. Let's say we got a can. Need to design a can. Now let's say the volume has to be 12 cubic inches. Well, how would they get 12 cubic inches? You figure out how many ounces you want to have in that can. If it's a 12-ounce can or a 15-ounce can or 11.75 ounce can or whatever it is. And for that many ounces, it's pretty straightforward to figure out how many cubic inches that is. That's something that you could do on one of the search engines. Just type in, convert 12 fluid ounces to cubic inches, and boom, it'll bring it right back. So that's a real easy thing to do. Okay, so we've got our volume. And what we want to do is we want to minimize cost. The objective, minimize cost. And as with the conversation we had earlier, minimizing costs means minimizing material, which means minimizing surface area. So if we're going to minimize the cost, we need to first compute what is the surface area of the can. Well, to figure out the surface area, let's figure out the parts. We have a top, we have a bottom, and then we have the side of the can. I don't know if you've ever paid much attention to cans, but cans have several rings on the top. I don't know if you've ever pulled the label off of a can. Cans are definitely not straight on the sides. In this middle area, it looks like this. Those rings on the top and the zigzags on the side are there for the same reason. Well, I thought the zigzags might be to make it easier to hold onto the can so it doesn't slide in your hand. Well, the only problem with that is there's a label over it. So do you really feel the zigzags? Unless you go and really crunch down on that thing? Probably not. Any idea why the zigzags and the rings are there on the can? Make it fancier? Never really thought about a can before, Chuck. The reason they do that is it strengthens it. So when you grab the can by the side doesn't flex in. It's rigid. And it's cheaper to use a thinner wall that's zigzagged than to use thicker material that won't flex as readily. So what they've even done on the cans is they've figured out we can save 1/1000th of an inch in thickness if we zigzag it. And overall that winds up saving us material versus making the walls thicker without the zigzag. They've gone kind of crazy on this stuff, haven't they? Was it a national conference a couple years ago, and one of the folks that was speaking was an engineer for Campbell Soup. They use engineers to make soup? Yep. He was talking about the cans. And his comment was, if you can find a way to make a can that uses less material than the can they've got right now, Campbell Soup will cut you a check right now for $2 million to give them those dimensions. Write down the dimensions, hand it to them, they'll check it out, boom, you're a millionaire. Why is it worth millions to them? Just get a couple of numbers. Because they're doing this 7 billion times a year. If they can save a little bit times 7 billion, that's a huge savings. They'll very quickly get back the $2 million that they just gave David, for figuring this out. Okay, we're going to ignore the zigzags. We're going to ignore the rings. We're just going to pretend they're flat surfaces for now. We're going to do surface area. What's the formula for the total area of the top of the can? Well, let's see, what shape is the top? What shape's the top of the can? A circle, isn't it? So that means that the top is going to have an area, pi r squared. The bottom's the same thing, pi r squared. And then we've got the side. Now, on the side of the can, let's see, and Jacob, here's your test. I'll get that back. You're allowed to do full corrections. They're due Friday. Okay, so here's our can. On the can, got the paper just folded into a cylinder. For a can, you have a height, and in addition to that height, you have the circumference, don't you? Those are the two measurements on a can. Well, when they make these cans, this side of the can, any idea what shape this is when it starts out? You ready? Whoa, look at there. It's like magic. The side of the can is really a what? Just a rectangular piece of metal that's been folded around. Okay? So what's going to wind up happening is this side of the can is nothing but a rectangle. It's going to have a height to it. And this piece up here, which would in this shape be called the length, is the circumference. The circumference, the formula for circumference, is the derivative of the area of the circle. There's a relationship there. We're not going to chase it down right now. But if you ever forget the circumference, just remember it's the derivative of the area. Well, what's the derivative of pi r squared? Well, pi is just a number. R is the variable. If it was x squared, the derivative would be 2x. Oh, this will be 2r. Oh, and there's a pi in there. So it's going to be 2 pi r times whatever the height is. We can combine a couple of these terms, the top and the bottom. We're going to have 2 times pi r squared plus 2 pi r h and we're in the same position as we were in the previous problem. We have 2 variables, the radius and the height. To play the game the way we know how to play it, we've got to get it down to just one variable, don't we? But you already know how to do that. We can use this information about the volume. The volume is going to be anytime you have a container where the base is perpendicular to the height, the formula for volume will always be whatever the area of the base is times the height. So if it's a star-shaped thing, you figure out what the area of the star is, multiply that times the height, and you've got the volume. It's like stacking up a bunch of cookies or Pringles or something like that and adding them all up to get your volume. So the volume is going to be pi r squared, that's the area of the base, the circle, times the height, and we want this to equal 12. As we did with the previous problem, we can solve for h. H is going to be 12 divided by pi r squared. We can take this and substitute it in there. This gives us then a formula for surface area that's going to be 2 pi r squared plus 2 pi r times 12 over pi r squared. We can do a little cleaning here, a little canceling. The pi there and there will cancel. One of the r's, this one and that one, will cancel. This then gives us the formula 2 pi r squared plus 24 over r. Does it make sense where the r comes from? You have the 2 here times the 12 there, which will give you your r. This can be rewritten as 2 pi r squared plus 24 r to the negative 1. I'm rewriting it because now that we have the formula for the area, we're going to compute the derivative. And it's easier to compute the derivative, or at least for me it's easier to compute the derivative of 24r to the negative 1 than it is to do 24 over r. Okay? Once again, how much calculus have we done so far? None. You ready? It's calculus time. The derivative of the surface area is going to be 4 pi r minus 24 r to the negative 2. So far, so good? We compute the derivative. The derivative can be rewritten as 4 pi r minus 24 over r squared. And once we get our derivative cleaned up, we can set that equal to 0 because we need to compute a value for the radius. This gives us 4 pi r equals 24 over r squared. As we did with the previous problem, we can multiply both sides by r squared. Before we were multiplying by L, but you get the idea. This will give us 4 pi r cubed equals 24. Solving for the r cubed, we get 24 over 4 pi. We can take the cube root of each side, and what we're going to have is the cube root of 6 over pi. The 24 and the 4 reduce. So we have the cube root of 6 over pi. As with the previous problem, you can't exactly go to Lowe's and say, hey, I need the cube root of 6 over pi, whatever it is. We need to convert this back to something or other in terms of a decimal. So I'm going to do 6 divided by pi, parentheses, raised to, parentheses 1 divided by 3. What I wound up doing is in the calculator I did 6 divided by pi raised to 1 divided by 3, so that gives me the cube root. It's not the only way to do it, but it's the way I worked it out. This will then give us that r equals 1.24 inches. Now remember, this is not all the way across. This is the radius. That's only halfway across. That means the diameter is about 2.5 inches. Make sense? So the radius is going to be 1.24 inches. The diameter will be 2.5 inches. What's the height of this can going to be? Let's see. Let's go on back up here. Here we are. The height is way up here. It's 12 over pi r squared. So we can bring that on down here. It's going to be 12 divided by pi r squared. So that's going to give you 12 divided by pi times 1.24 squared equals. Okay, so we have 12 divided by parentheses pi times 1.24 squared parentheses gives 2.48. Is that making sense to everybody? Okay, so the can in its finished form, looking at the time, in its finished form, the can is going to have a diameter of 2.48 inches. Whoa, look at this. And a height of 2.48 inches. That's about the size. I don't know if you've ever looked at them or not. Buy tomato soup, they have tomato paste, tomato sauce, all that stuff. The tomato paste cans are the real skinny ones. But next to them is the tomato sauce. That's about the size of a tomato sauce can. Not as big as a soup can. Soup holds more than 12 cubic inches of material. We really don't have time to prove that it is a minimum. It is a minimum, okay? And there you have it. So we cruise through 2 of them. Friday, I have a paper for you, and we'll work on a couple of those. We'll get more into inventory type problems, more into controlling costs. Ah, yeah, there's something they're going to be concerned about. Things of that nature. Remember, Friday, you have the opportunity. Do you have to do this? No. If you want to, you can turn in test corrections. You can do up to 4 parts, like part A would be 1 part. Part B would be 1 part. Things like that. Okay? Rings good? I'll see you Friday. I hope you have a good day.